never stop optimizing, no matter the circumstances. And if you don't find my lectures inspiring enough, you can always get inspiration from Bill Gates. At least I do.
This because there's more bang for your buck is not inspiring, Bill.
Well, that's too bad. It's not my goal to be inspiring. The world has limited resources.
So if you're not doing things to be inspiring, what are you doing things for?
Optimization.
Okay, previously we talked about the general purpose techniques for generating valid inequalities or cuts for integer programs, and before we assumed that all the variables involved were integer. In this lecture we will discuss a more general case when we also have continuous variables, so we'll talk about the mixed integer cuts. And we'll talk about three techniques for generating mixed integer cuts for general mixed integer programs. First, we'll start with the Gomory mixed integer cuts. Then we'll talk about the mixed integer rounding inequalities. And finally, we'll talk about the disjunctive cuts. Okay, so the problem that we are focusing on in this lecture is the following mixed integer program. So we assume that we have integer variables given by the vector x of length n1, and we have continuous variables given by the vector y of length n2, and the objective is given by C transposed x plus D transposed y, and the constraint matrix consists of two parts. The part A corresponds to the coefficients for x, and the part D corresponds to the coefficients for y. Alright, so now recall how we generated the Gomory cuts. We essentially took the optimal solution to the LP relaxation, and then we looked at the values of the basic variables. If all the basic variables are integer, then we are done. If there are fractional variables in the basis, then what we do, we apply the Gomory cut based on the row in which the basic variable has a fractional value. Okay, so if we try to apply the same logic for mixed integer case, so let's see what is happening in this case. So now the simplex row in our case is going to look like this. So you have xr, assume that we are talking about the row r, where xr is the basic variable, and we have two sets of non-basic variables. So the first one is given by n1, so these are the non-basic variables corresponding to the integer set, and the set n2 corresponds to the non-basic variables from the continuous set. And by the way, this assumes that we already added slack variables, and the slack variables would belong to this set here where you have yj's. Okay, so because in general the slack variables in this case can be continuous, so assume that these slack variables are included in this part right here. So we have the coefficients arj bar for xj's, the coefficients drj bar for yj's, and then the right hand side is given by br bar, and the assumption is that br bar is not integer because we only need to take care of the variables that are fractional. Alright, so now let's see what we can do to this equation here. So previously with the Gomory cuts, what we did, we essentially rounded down all the coefficients for the integer variables, and we said that this is going to give us a lower bound on the left hand side. Therefore, instead of writing equal here, we'll write less than or equal to after rounding down the coefficients for xj's. But there is an issue with the continuous variables, because in the Gomory's cut, the next step that we would take, we wouldn't have this part right here, so therefore we would say, okay, this is integer, and the right hand side is fractional, but you know, if you round down the right hand side, then we'll obtain a valid inequality, right? So, but in this case, because we have this continuous part as well, we cannot round down BR anymore, because if we do, then we can cut off some part of the feasible region that now is feasible because we allow the non-integer values for these variables yj's. Okay, so we need to analyze this in more detail, obviously. So we cannot just do the same we have done in the pure integer case. And let's look at some very simple cases first, and then we'll build on that and we'll analyze the more general cases. Okay, so first, assume that I have this basic variable x, let's say, the fractional right-hand side b, and then we have just one continuous variable y with some coefficient a. And by the way, this coefficient here doesn't really matter because, so we could have had just a equal to 1, because we're talking about the continuous variables here anyway, so I could have substituted this for just some variable y prime, let's say, right? So then we just have x plus y prime is less than or equal to b. So, but let's keep it general, and we'll just assume that a is a positive coefficient here, and then we'll analyze the case when it is negative separately. Okay, so if we have an inequality like this, x plus ay is less than or equal to b, then this is the feasible region for the LP relaxation, and then these lines here correspond to the feasible points for our mixed integer program. So remember, x is the integer variable, y is the continuous variable. Okay, so now we can clearly see that one of the corners is fractional, so this is because the value of b is fractional. So therefore, what we are going to do, we will cut off this corner and see, we only need to worry about x being integer now, y, the fractional value for y, doesn't matter. To cut off this corner, what we need to do, we essentially just forget about ay here, and if x plus ay is less than or equal to b, and both a and y are non-negative, then clearly x less than or equal to b is going to be a valid inequality, and then because x has to be integer, we can round down b, and we obtain the cut x is less than or equal to floor of b. Okay, so and now we have a perfect description of this polytope representing the convex hull of all the feasible solutions for our mixed integer program. Okay, so now let's look at all other possibilities of what can unfold here when we just have two variables, and the variable x, the integer one, is the basic variable that we need to take care of. So now let's look at what happens when we reverse the inequality sign here. This situation is a little more interesting. We have two corners here. One is feasible because we don't need to worry again about the integrality of y is a continuous variable, and this corner is not feasible because b is fractional and we need to have integer x. Okay, so and now we can see how we can cut off this fractional point. So all I need to do is to draw the line here between this point right here and this point right here. So if I add the cutting plane passing through these 2 points, then we'll cut off the fractional corner, and again we'll have a perfect description of the convex hull of all the feasible solutions for our mixed integer program. Alright, so now all we need to do is write down the inequality corresponding to this line passing through these 2 points, and looking at what points we have here, so the x coordinate for this point is the floor of b, and then the y coordinate is going to be given by f over a. And for the second point, the x coordinate is the ceiling of b, and the y coordinate is 0. So essentially we have these 2 points, and we'll generate the cut by writing down the corresponding inequality. And this inequality is going to be given by x plus a over f y is greater than or equal to the ceiling of B. Alright, and next we are going to consider the remaining possibilities here. So the next possibilities will be having minus right here in both cases. Okay, so let's analyze them one by one. So now when we have the inequality x minus ay is less than or equal to b, then we have the following feasible region, and we have again a similar situation. So there is a corner that's fractional, and we need to cut off this corner by introducing the cutting plane that passes through these 2 points right here. Alright, so the first point would be the floor of B, 0, and the second point would be the ceiling of B, 1 minus f over a. Alright, so we have these 2 points, and the corresponding inequality will be x minus a divided by 1 minus f times y is less than or equal to the floor of B. Okay, so this situation is actually similar to the case that we just considered. So let's compare these two. So here we have x plus a over f times y is greater than or equal to the ceiling of B, and here we have x minus a over 1 minus f times y is less than or equal to the floor of B. Okay, so finally the last case that we need to consider is x minus ay is greater than or equal to b. In this case we have a simple situation similar to the first case that we considered. So again the cut is very simple. So here you have negative ay, and if we just remove this part right here, then clearly we'll have a valid inequality, and then again because of the integrality we can round the right hand side up and we'll obtain a valid inequality, and this is the cut that we obtain. Okay, so a very simple one. Alright, this summarizes all the 4 cases we considered, and out of these 4 cases only 2 are really interesting, and the first one and the fourth are trivial. So we are going to see next how these developments can be used in a more general setting. So we're going to go back to the simplex row that we've seen on the first slide, and we'll try to analyze how we can use these cutting planes for the simple 2-variable case in a more general setting. So let's take a look at our simplex row, and let's introduce some notations here. So we'll be concerned with the fractional parts of numbers, so therefore we'll use frj for the fractional part of arj bar, so which is arj bar minus the floor of arj bar. And let's denote by fr the fractional part of br bar, which is br bar minus the floor of br bar. Okay, so if we work just like we did before with the Gomory cut, then we would round down the coefficients for xj, and then to take care of the continuous part here, here we copied the 2 interesting cases from the previous slide, and we are going to use these formulas to address the continuous variables. Okay, so we can write down xr plus the summation for j in n1 of arj bar, the floor, times xj's, and then plus the summation of all the drj bars yj's equal to br bar. So now actually we have less than or equal to, because we rounded down the coefficients for our variables xj's. Okay, so now we can treat this as a single integer variable, and we can treat this as a single continuous variable. So this is how we can take advantage of these simple formulas that we developed for the two-dimensional case. So we will essentially treat this part of the equation as the integer variable x in this formula right here. As for the continuous variables, we will ignore those continuous variables for which the coefficient drj bar is positive. Then this is essentially similar to rounding down, right? So the value of the sum can only drop in this case, and therefore the inequality will remain valid. And then what we'll do with the negative coefficients, we will treat them essentially as negative y in our formula right here. So think of this formula applied to this case, where the negative y will be given by only the negative parts of this sum, and then your a is going to be equal to 1, and we are going to apply this formula. So let's write it down. So for x, we will have xr plus the summation for j in n1 of the floor of arj bars xj's, and then we are going to move the y part, this part right here, to the right hand side. So you'll write down less than or equal to the floor of br bar, and then minus the summation for j in n2. Actually, let's denote by n2 minus the set of j's such that drj bar is negative, and then we'll have drj bars yj's divided by 1 minus f, and in our case f is actually fr. So, and let me record this notation. So n2 minus would be the set of j's in n2 such that drj bar is less than 0. Alright, so this is clearly a valid inequality, but we are going to try to slightly strengthen this inequality. So, and the motivation is as follows. If this fractional part for arj's is kind of small, then rounding down doesn't hurt you much in the left hand side. So generally, to have as tight as possible inequality, we want these coefficients here to be as large as possible, right? So by rounding down, we lose somewhat in the tightness of the constraint, right? So, but then our hope that the right hand side is gonna drop even more, and therefore rounding down makes sense, and we cut off a part of the region that's feasible for the LP relaxation, but is not feasible for the convex hull of our mixed integer program. Okay, so now thinking about it, so what if the fractional part of arj is pretty large here? Then, if it is larger than the fractional part for the right hand side, then maybe rounding down is not such a great idea, and maybe we should try to keep the coefficient for this variable as it was before, and essentially treat this variable in a way similar to how we treat the continuous variable. So essentially move it to the continuous part, and let's see what happens. Alright, so, and again, this will probably make more sense when the fractional part of the coefficient arj bar is kind of large, so it's larger than the fractional part of the right hand side. To distinguish between the coefficients with relatively large and relatively small fractional parts, we are going to introduce the following notation for convenience. Let's denote by n1 less than or equal to the set of j's in n1 such that frj is less than or equal to fr. So these are the coefficients for the variables such that the fractional part of these coefficients is less than or equal to the fractional part of the right hand side. And then n1 greater will be the set of j's in n1 such that frj is strictly greater than fr. So these are the coefficients with relatively large fractional parts, and these are the coefficients that we are going to use in a way we are using the continuous variables here in our equation. So for now, let's actually drop all of these derivations here. So let's forget about this for now. And we are going to start developing an alternative formula that will be tighter, right? So we are going to split this sum into two, corresponding to the index set n1 less than or equal to and n1 greater respectively. And then for the variables corresponding to n1 less than or equal to, we are going to treat them in exactly the same way as before. Whereas for the remaining coefficients, we'll use a different way of representing them. Alright, so you'll have xr plus the summation for j in n1 less than or equal to arj bar rounded down times xj's. And then for the variables in the second set, j belonging to n1 greater, going back to the original equation here, we'll essentially use arj bar the way they were before. So, but what we're gonna do, we will represent arj bars as the difference of the ceiling of arj bar and 1 minus the fractional part for arj bar. 1 minus frj. Alright, so we didn't really change anything about the coefficient for xj. And then we still have the summation of j's in n2 of drj bars yj's, and all of this is going to be less than or equal to br bar. Alright, so now going from the original equation to our inequality, what we changed, we rounded down the coefficients for xj's. Alright, and we didn't round down the coefficients for xj's in the set of j's given by n1 greater. Okay, so those coefficients with relatively large fractional parts, they were not rounded down, so instead we just wrote down their equivalent representation as this difference right here. And what's particularly important about this representation is that the coefficient for xj, this part is negative. Okay, so we are gonna split this coefficient into two parts. The integer part will go towards this sum, and then the fractional part is gonna go towards the continuous variables. Okay, so this is how we are going to apply this formula right here for our case. Now the y part will essentially consist of the fractional part of this sum and also the sum of yj's for j where drj's are negative. Alright, so then we can apply this formula right here. So writing down the x part of this formula, we'll have xr plus the summation of the floors of arj bars multiplied by xj's for j in n1 less than or equal to, then plus summation for j's in n1 greater of the ceiling of arj bar times xj minus 1 minus frj multiplied by xj, the summation of this for j in n1 greater, plus the summation for j in n2 minus of drj bars yj's, and all of this must be divided by 1 minus fr. So let's put plus here, and then I can put all of this (1 minus fr), and this is less than or equal to the floor of B. So now regrouping the coefficients for xj in the set n1 greater, we can simplify this formula. So for this part we still have the same expression, so xr plus the summation for j in n1 less than or equal to of the floors of arj bar xj. And then for the set n1 greater, we'll have the following coefficient for xj. So we have the ceiling of arj bar coming from this part, and then minus 1 minus frj divided by 1 minus fr, and this all is the coefficient for xj. And then plus the summation for j in n2 minus of drj's bar divided by 1 minus fr multiplied by yj, and this is less than or equal to b. So finally we can simplify this part right here. The ceiling of arj bar minus 1 gives us the floor of arj bar minus the ceiling of arj bar multiplied by fr, and minus frj, and all of this divided by 1 minus fr. Finally, we will represent the ceiling of arj bar as the sum of the floor of arj bar and 1, and we'll simplify this expression to the following. So it's gonna be arj bar, the floor of it, plus frj minus fr divided by 1 minus fr. Alright, so and now we will use this expression in place of this one in the formula above. So this we'll go in here to obtain the final version of this formula of the cut that we are going to obtain. So we have xr plus the summation for j in n1 less than or equal to of the floor of arj bar xj, then plus the summation for j in n1 greater of the floor of arj bar plus frj minus fr divided by 1 minus fr. All of this multiplied by xj, and then finally the summation for j in n2 minus of drj bar divided by 1 minus fr of yj, and all of this is less than or equal to the floor of b, and this is the Gomory's mixed integer cut. Alright, going back and comparing it to what we had before, the difference is in this part right here. So here you just round down the RJ bars, right? So, but now for some of RJ bars, in particular for those for which the fractional part is greater than that of the right hand side BR, we replaced the floor of ARJ bar with something slightly greater. So you can see that because FRJ is greater than FR, this is positive, and then divided by 1 minus FR will only make it greater, alright, and this is definitely greater than ARJ bar floor. So as we can see, we obtain a better valid inequality, alright, and in particular this valid inequality, the Gomory mixed integer cut, is known to be extremely efficient. So this is probably the most important general purpose class of cuts for mixed integer programming. Okay, so and in fact you also get improvement for pure integer programming, because all of this can be applied for pure integer programming as well. So you could strengthen the inequalities that you have in Gomory cuts by applying this trick right here, and instead of ARJ bar, the floor of this, you will have a higher coefficient. Alright, going from this weaker valid inequality to the Gomory mixed integer cut is nothing else but the application of what is known as mixed integer rounding. So this process, applying this trick when you replace the floor of ARJ bar with a slightly stronger coefficient, was later known under the name the mixed integer rounding. So Gomory was the first who actually applied it, but he applied it to the row of the simplex tableau. Applying it in a more general setting has the name of mixed integer rounding, or mixed integer rounding inequalities, and this is the next topic of the discussion. Alright, mixed integer rounding. We actually used it already to derive the Gomory's mixed integer cuts, and in fact this inequality follows directly also from these elementary inequalities in 2 dimensions that we considered earlier geometrically, and this is exactly what we used to develop the mixed integer Gomory cuts. But now we are going to establish the mixed integer rounding inequality in a setting that is more compact on the one hand. Here we have only 3 variables, and is quite general on the other hand, because the way these variables are, we look at one variable with the rational part that is less than or equal to the fractional part of b, and the other variable has the fractional part that is greater of that of the right hand side. Okay, so we have two integer variables x1 and x2. We have a continuous variable y, and we introduced the notations for the fractional part of b, so we denote it by f, and then we have the fractional part of the coefficient for x1 and x2 is denoted by f1 and f2 respectively, and the assumption is that f1 is less than or equal to f and less than or equal to f2. So the fractional part of the right hand side is sandwiched between the fractional parts of the first coefficient and the second coefficient. The motivation behind the mixed integer rounding inequality is that we don't want to round down the coefficients for the variables that have a large fractional part. In particular, here, the second coefficient has a fractional part larger than that of the right-hand side, and we don't want to round it down, so instead we want to split that coefficient into two parts. The first part will be the ceiling of A2, and the second part will be 1 minus the fractional part of A2, and this second part comes with a negative coefficient, so and then we will move this fractional part multiplied by x2 into the set of continuous variables essentially. So we'll treat this part as a continuous part of our inequality, and this will allow us to generate a stronger cut. Generate a valid inequality, we go ahead and round down the coefficient for x1. Recall that a1 has a smaller fractional part than the right hand side does. And then for a2, we replace it with the difference of the ceiling of a2 and 1 minus the fractional part of a2, just like we specified here. And we do the same thing for b actually. B is also represented as the difference of the ceiling of b minus 1 minus fractional part of b. Alright, so and then we keep y unchanged, we just move it to the right hand side. And next what we are going to do, we'll regroup the terms in this inequality so that all the integer parts are on the left, including the constant, and all the fractional parts are on the right. So essentially we treat this 1 minus f2 times x2 as a continuous variable, and we'll consider it together with y here. And also the fractional part of b, or to be precise, 1 minus the fractional part of b is involved in the right hand side as well. So as a result, this is what we obtain. So we have everything is integer right here, and everything is fractional or can be fractional in the right hand side. Okay, so now we'll consider a couple of different possibilities. So the first possibility will be when this left hand side here is non-negative. So when it is non-negative, if we multiply it by a positive scalar that is less than 1, then we will still obtain a valid inequality, because the left hand side can only decrease, and this inequality will still hold. Alright, so and then we will derive the mixed integer rounding inequality based on this trick, and then we'll consider the second case when the left hand side is negative. So when it is negative, then clearly we cannot apply this trick, but in that case we will show that trivially the inequality that we will derive, this mixed integer rounding inequality, will still hold. Alright, let's go ahead and look at these two cases in more detail. So this is what we ended up with on the previous slide. And now, as we mentioned, we are going to assume that the left hand side is greater than or equal to 0. And then when it is greater than or equal to 0, then multiplying it by 1 minus f, which is a positive number between 0 and 1, is not going to change the validity of this inequality here. So because the left hand side only decreases and the inequality will still hold. Okay, so and Now rearranging the terms, moving the x2 part to the left, we will obtain finally the mixed integer rounding inequality, which is what we want to establish. Okay, so here what we used is the observation that the ceiling of A2 is given by the floor of A2 plus 1, and the same thing holds for the ceiling of B, so it's also replaced with this floor of B plus 1, and then the simple algebra leads us to this inequality here. And when you look at the form of this inequality, it's pretty straightforward. So whenever the fractional part of the coefficient for a variable, for an integer variable, is smaller than the fractional part of the right hand side b, then we just round it down. We round down the corresponding coefficient to the closest integer. And in the case when the fractional part of the coefficient for the integer variable is greater than that of the right hand side, then we don't just round down, but we add also this small positive term to the round down of A2. So it's given by F2 minus F divided by 1 minus F, and clearly F2 is less than 1, so therefore this ratio is actually going to be less than 1 and greater than 0. So it's between 0 and 1, and it's strictly positive. So we obtain a strictly stronger inequality than if you would just round it down A2 here. Alright, and on the right we obtain the floor of B plus y divided by 1 minus f. And, you know, again, we could have just used this inequality, the elementary inequalities that we derived geometrically, but I wanted also to go over the algebraic proof here so that it is more complete, okay? So we established this inequality, but not quite completely yet, because we still need to consider the second possibility. So here we assumed that the left-hand side was greater than or equal to 0, but now let's see if the inequality still holds when the left-hand side is less than 0. Note that when it is less than 0, then this doesn't work anymore, so we cannot multiply by a positive number that is less than 1 and still claim that the left-hand side decreases. So therefore, we need to treat this case separately, but then if we look at the left-hand side of the inequality in the case when it is less than 0, then because it is less than 0, so this means that the floor of A1 times x1 plus the ceiling of A2 times x2 is less than or equal to the ceiling of B. Not less than or equal to, but strictly less than the ceiling of B. And because this sum is integer, this means that it must be less than or equal to the floor of B. And if it is less than or equal to the floor of B, then obviously if we replace the ceiling of A2 with something smaller, because x2 is positive, the resulting inequality will also hold. And this is what we essentially do to obtain the mixed integer rounding inequality. What's the difference between this right here? The difference is in the coefficient for x2 and an extra positive part y divided by 1 minus f. So obviously adding y divided by 1 minus f will only increase the right hand side here and the inequality still hold. And then replacing the ceiling of A2 with the floor of A2 plus this ratio is also going to only decrease the coefficient for x2 because look, this ratio here, it cannot be greater than 1, so it's in fact less than 1 always. And therefore this inequality holds, and by replacing the ceiling of A2 with this expression, we only decrease the left-hand side, and therefore if this inequality holds, then the mixed integer rounding inequality will also hold, and the proof is complete. So next we'll consider an example of applying the mixed integer rounding cut to a pure integer program. So this is the same example as we used to illustrate the Gomory cut. And in fact, when we apply the mixed integer rounding cut to the row of the simplex tableau, then it's exactly the same as Gomory mixed integer cut. And this example will also illustrate how we obtain the improvement with Gomory's mixed integer cut compared to just the Gomory cut, even for pure integer programs. Alright, so in this case, the simplex tableau row that we were using to obtain the cut was x2 plus 1/7 s1 minus 4/7 s3 is equal to 16 over 7. And what we did, we just rounded down the coefficients for the non-basic variables, and then we obtained this inequality x1 plus x2 is less than or equal to 5, which was shown on the graphical illustration with this cut right here. Okay, so now when we apply the mixed integer rounding cut or the Gomory mixed integer cut to the same situation, let's see what we obtain. So first of all, we need to look at the fractional parts of the coefficients for the non-basic variables. For S1, we have 1/7 is our fractional part. Then for S3, it's going to be negative 4/7 minus negative 1, which gives us 3/7. And for the right hand side, f is going to be equal to 2/7. The integer part is 2, the fractional part is 2/7. We can see that one of the coefficients for the non-basic variables has a fractional part that is greater than that of the right hand side, and the other one has the fractional part that is less than that of the right hand side. So this is a nice example to use for the illustration. So therefore, when you write down the Gomory mixed integer cut or mixed integer rounding cut, which is the same thing in this case, we'll have x2 plus, for S1 we'll round down 1/7 to 0, so therefore S1 will disappear, and for S3 we will actually have the round down of negative 4/7. So the floor of this is going to give us negative 1. And next we are going to add this ratio. So remember, the ratio was f, let's call it f3 in our case. Let's fractional part of the coefficient for S3 will be f3. So it's going to be f3 minus f divided by 1 minus f. Alright, so in our case, f is given by 2/7. And this is our f3, it's 3/7. So what we'll have here in this ratio then is gonna be 3/7 minus 2/7, and then 1 minus 2/7. All right, so that's the coefficient that we get for S3. And then, for the right hand side, we'll have less than or equal to the floor of 16 over 7, which is 2. All right, so, and note that we don't have a continuous variable here, but still we treat a part of the variable S3 as essentially the artificial continuous variable. So essentially we treat it as continuous, and to obtain the mixed integer rounding cut. All right, so as a result, the equivalent expression will be x2. So this part is going to give us 1/7 divided by 5/7, so it's going to be 1/5. So minus 1 plus 1/5 will give us minus 4/5. S3 is less than or equal to 2. And then S3, we need to express it through the original variables in order to obtain an inequality that we can actually show on this plot. So it's going to be 3 minus x1, so we'll substitute 3 minus x1 for S3. So we'll have S2 minus 4/5, 3 minus x1 is less than or equal to 2. And this is equivalent to 4x1 plus 5x2 is less than or equal to 22. Okay, so now we obtain a new valid inequality, and it is actually stronger than the valid inequality that we obtained with Gomory cut. So look here, we had x1 plus x2 is less than or equal to 5, and it cut off some of the fractional points of the feasible region, and then we saw that it was actually this line was parallel to the isoprofit line. So, and even though with Gomory cut we did obtain the integer optimal solution, there were infinitely many other optimal solutions that were not integer, and therefore it was not an ideal situation. So now let's see what happens when we add this cut for x1 plus 5x2 is less than or equal to 22. So if we plug in the integer optimal point 3, 2 into this expression, we see that the line will pass through this optimal point, and obviously it's not going to be parallel to the isoprofit line, so we know that it's going to cut off the non-integer optimal points. Okay, so let's see how it looks like. So this is the cut that we add, and we see that now the integer optimal solution is the unique maximum here, and we obtained a stronger cut than with just a Gomory cut. Finally, I would like to conclude this lecture with a brief discussion of disjunctive inequalities and split cuts. Alright, so consider the situation when we have a disjunction of two sets. One is S prime, the other one is S2 prime. So this is a general situation. We don't necessarily talk about polyhedra here. But assume that the inequality, the summation of pi j primes xj's is less than or equal to pi 0 prime is valid for S prime, and the similar inequality is valid for S2 prime, with pi j 2 primes being the coefficients for xj's and pi 0 2 prime being the right hand side. So then, if we look at these two inequalities, and because all the variables are assumed to be non-negative, so see we have here Rn plus, then if you replace the coefficients for xj's with something that is no greater than the current coefficients, then obviously the inequality will be valid, right? So therefore, if you replace each coefficient for xj with the minimum of pi j prime and pi j 2 prime in any of these inequalities, then we'll obtain the valid inequality for either S prime or S2 prime. So essentially for both of them, right? So meaning that this will be a valid inequality for the disjunction given by S. Similarly, replacing the right hand side with the maximum of the two right hand side will still keep the inequality valid, and therefore this resulting inequality with minima here and the maximum on the right hand side gives us the valid inequality for the disjunction of the two sets. So it's easy to construct a valid inequality for the disjunction given two valid inequalities for the sets included in the disjunction. Alright. Next, we are going to look at the equivalent characterization of the valid inequalities in terms of the dual multipliers. And this is for the case of the polyhedral sets. So assume that we have two non-empty polyhedral sets. One is P prime, the other one is P2 prime, and they're given by the following equations. All variables are supposed to be non-negative, and we have A prime x less than or equal to B prime and A2 prime x less than or equal to B2 prime. For the systems of inequalities other than non-negativity. So now, if you want this inequality, which is given by the summation of pi j's xj's less than or equal to pi 0, to be a valid inequality for the convex hull of the disjunction of P prime and P2 prime, then this can be the case if and only if there exist vectors of non-negative multipliers u for the first system and v for the second system, such that these coefficients in the equation pi j is less than or equal to the minimum of u transpose times a prime, the jth component of this product, and v transpose times a2 prime, the jth component of this. So for each component we need to pick the minimum of these two. And what is happening here, so if you look at u transpose times a prime, this is like, think of the dual multiplier that we have for this system right here. So for each row in this system we are going to have a multiplier ui for I between 1 and however many rows we have here. And similarly for the second system we'll have the multipliers vi's and the number of multipliers can be different, so generally these inequalities can have different number of equations, but in the end, when we multiply, what we'll have is the vector of length n, of length which is exactly equal to n, the number of variables that we have. Alright, so and again, we pick the minimum for each component, and for the right hand side we pick the maximum of these multiplier vectors multiplied by the right hand sides of the respective system. So we pick the maximum of the two, and this statement can be proved in a relatively straightforward fashion by just using the duality theorem. And here is the illustration for this example here. So let's say in a case like this, so here we have the valid inequality for the disjunction, and we can see that it passes through extreme points of the respective polyhedral sets, and the multiplier vectors u and v here would be given by the optimal dual solutions for the corresponding LPs, where the objective would be exactly this line right here. So this would essentially be the isoprofit line for the objective, passing through the optimal corners of the feasible region. Finally, we will mention how the disjunction can be used to generate cuts for mixed integer programming in a systematic fashion by applying the so-called split disjunction cuts. Alright, so assume that you have this polyhedral set right here, and there is a line or some hyperplane cutting through this feasible set. Okay, so if you assume that pi is an integer vector and pi 0 is an integer scalar, then clearly for every integer solution in the set, pi x must be integer and is gonna be either less than or equal to pi 0 or greater than or equal to pi 0 plus 1, right? So it cannot be fractional, cannot be in this set here in between. Alright, so therefore, by applying this split, we divide the feasible region for integer problem into two parts. Okay, so we divide it into these two parts right here, and then we can apply a disjunctive inequality to generate a cut for the original feasible region, and we'll cut off this corner right here that doesn't contain integer points. And a split disjunction can be shown to contain all the other cuts we discussed so far, so this is a very powerful technique that generalizes the previously obtained results. Then similarly to quatal closure, there is a concept of the split closure where you apply the disjunction cuts in a systematic fashion. So if you apply multiple rounds of split disjunction cuts, then the minimum number of rounds that you need to apply in order to obtain the perfect description of the convex hull of the integer points within your polyhedron is called the split rank of your polyhedron. Alright, so for integer programs, because these cuts contain the Gomory cuts, we can show that every polyhedron will have a finite split rank, but this is for the pure integer case. In mixed integer case, there are examples that demonstrate that the split rank may not be finite in some cases, but for example, if your objective only depends on the integer variables, and in this case the finiteness result still holds. And this is it for today. Remember to do the homework so that you are ready when it matters.
If we start now, we can be ready for the next epidemic. Thank you.